Good afternoon. How many people have located the Chinese antecedent to Pascal? So there's something called, I guess everyone who's studied in North America or Europe, well, it's maybe more widely known. Essentially everyone knows what Pascal's triangle is, right? Pascal's triangle is, it starts off, well, every journey starts with every journey starts with a single step. Whether it's 1,000 steps or, okay, but with Pascal's triangle, you start with a single point, and then what? Chikang, what's the second stage? Yeah, okay. You don't tell me the whole story. That's just tell me what's next. So you have a single point, and then what? Oh, 2 point. Oh, okay, 2 points, and then you can. Well, of course, you connect. Every point gets connected to the 2 points on either side of it below. You sort of the rows are skewed, right? So just like the seats in an auditorium, if you are moving seats, so these seats maybe are not like that. They're just lined up in a straight line. But if you have movable seats that you put in place and then put them away afterwards, I think it's common to have the two adjacent rows. The seats are staggered so that you have to go 2 rows before you get another chair in the same place. Otherwise, it's halfway in between. And I guess this makes it easier to see, especially if it's flat, the floor is flat. I know this because when I grew up, the floor was flat. I'm not saying the earth was flat, but by the way, anyone can tell the earth is flat. If you stand on a hill, I think you can see. Not just things, if you're looking over the water, not just things disappearing in the distance. But you can, I imagine that you can see you can see something round. You can see some roundness. Anyone ever notice that or agree with me? Of course, my imagination might be running away with me sometimes. But okay, but and then what's the are you no you what is your name? Please remind me of your name. Is it Vincent? Okay, good. I got it out first, right? Almost not almost too late, almost too slow. Okay, but that happens to me quite often. Almost too slow. Either that or too slow. Okay, but so what's the next row? Remember the flat auditorium. Remember the flat floor. Okay, so well, are you familiar with what's called Pascal's triangle? Okay, well you have 1 point, and then usually below that you have 2 points, sort of symmetrical. All right, but then at the third row, 3 points in the third row, right? And furthermore, it's symmetric, which means staggered with respect to the second row and lined up exactly with respect to the first row. And okay, but I know for a fact that this was discovered, I mean, several hundred years ago in France, but I believe several hundred years before that in China. I guess I would say it's an interesting historical exercise. Just look up Pascal's triangle Chinese with a question mark. Probably don't need the question mark. I used to be very slow looking things up, but now it's kind of a hobby, choosing keywords, and well, still slow, but it's fun to choose to 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 try to think of efficient keywords, or even keywords that work at all. Sometimes you have quite a lot of ways of choosing keywords, look something up. Be interesting to see what the Chinese context was. I think Pascal's context of probability. It'd be nice to see how it goes, but it's quite fundamental in C-star algebra theory. The example of Pascal's triangle, and how this leads in a natural way to a C-star algebra. And since the and if it's a C-star algebra, then it leads in a natural way to a group, right? The K0 group. And it's an interesting question both what the C-star algebra is and what the group is. It's a Melian group. It's an ordered group. The ordered group means you have different. Two elements might be comparable. One of them might be less than or equal to the other. If you say which elements are positive or greater than or equal to 0, then that tells you in general, since you assume the order is translation invariant, tells you when two elements are comparable, because you can always subtract to make one of them 0. And that's supposed to have the same comparability relation then. Okay, so I'm just sort of I'm just sort of drawing to your attention that this is a important example to study and to think of how you get the I mean the diagram is quite schematic, right? So you have to decide how it actually gives rise to a C-star algebra or an ordered group. So what's the legend? What's the key? Well, if you have a single point, I was already last time I was using a single point to denote a full matrix algebra, right? A single full matrix algebra. It was a schematic representation of the algebra, unspecified size. You put you put a number beside the point, and that would tell you what the order or size of the matrix algebra was. I mean, that would be one way of keeping track of it. And okay, and so, and if you have 2 points in one row, well, so one row is supposed to be a whole algebra, and if it's single point, it's a single full matrix algebra. If it's 2 points, then it's the direct sum of two full matrix algebras. And how do you tell what the size is? What's the legend or the key for how you read this as a map? Well, I guess a point should be non-zero. It should be a non-zero matrix algebra. If you don't specify, maybe it's 1 by 1. Maybe it's 1 by 1 matrix. And then so you start with a single point. That could be the algebra of complex numbers. And then if you have 2 points at the next stage, let's make it symmetric. Okay, and well, it's difficult to line up to join the points. Okay, not all. Well, in this case, all the points between the two different rows, all the pairs of points, and if you have a single line in a Bradley diagram, that's supposed to have matrix algebras, two matrix algebras at the next stage. But if you have a single line, that means that the map from the first algebra, first full matrix algebra into the second one is just multiplicity 1, okay? And what does multiplicity 1 mean? It means that if the first algebra is the complex numbers, and it's a unital map, then the second algebra is also the complex numbers, and it's an isomorphism, okay? So, so the second algebra is the direct sum of two copies of the complex numbers. See, I'm going to run out of space. I hope I stay on the camera. Okay. All right. And then the as Vincent was saying, Chikam was saying 2 points at the second stage. Vincent was saying 3 points at the third stage. Notice we're not actually making a full triangle. So the triangle, saying triangle is a bit of a misnomer. You have to imagine the 3 points forming a triangle. You always have 3 points. But it's what's important is the two sides of the triangle. So every point maps. It's joined to the 2 points on either side of it. Okay. And so if it's supposed to be a unital map, these are finite dimensional algebras, finite direct sums of matrix algebras. And so if it's multiplicity 1, this is the complex numbers, then the first one and the second one will both be copies of the complex numbers. But at the next stage, the first algebra, well, if it's unital, the unit is the direct sum of the units at every stage. So the unit here will go down to the unit here. Well, because nothing else is going into it. That's the only way that the unit in the whole second algebra can map into the unit of the whole third stage. So we get a copy of the. I'm going to have to continue over here. We have C and then C plus C, and then on the outside we have C again, and both ends. Okay. But then what do we have in the middle? There's a big space in the middle. What's the algebra in the middle? How many people? I would. I don't mind someone who already knows answering, but I would prefer to see someone who doesn't know. I mean, I think that for one thing, I think it's important to. Charlie, you don't. Are you sure you don't know? Okay, I exactly like to see people guessing. Okay, they don't jump into the blue. Of course, you should look before you leave, right? Yeah. Okay. Well, no. The convention is that every row is a direct sum of full matrix algebras. Okay. So definitely the middle algebra is the direct sum of three. It's a direct sum of three matrix algebras, and the only question is how large they are. Okay. And the point is that each of these 1 by 1 is mapping with multiplicity 1 into a 2 by 2, but not unitally, because the one here and the one here, this mapping, I guess the whole algebra mapped into here. Then if it's a homomorphism, these two projections or these two units in these direct summands are orthogonal. The product is 0. That's going to be true when you map the second algebra to the third algebra. The images of the two units in the two direct summands at the second stage, images are going to be orthogonal here. So if you have what's an example of a matrix algebra where you have two projections that are orthogonal, non-zero projections? Yes. Okay. How many people don't know? That'll eliminate. That'll narrow the field a little. I hope. Okay. Everyone knows. Larry, what did you say? Well, that's very good. That's 90% right, because I didn't ask for the codomain, I just asked, I could have been asking for the image, right? So you have this algebra mapping into this algebra. And of course, it can't be, if it's commutative, if it's homomorphic image of a commutative algebra is going to be commutative, right? So the image of this, if it's C squared, or C plus C, the image will be C plus C. But this is supposed to be a full matrix algebra. So you've got to have a C plus C sitting in a full matrix algebra. So that's you're missing 10%, at least 10%. Okay, but very good guess. Okay, I hope it was a guess. Sorry. Yeah. Okay. Good. Yes, Charlie, you want to come back to it? Okay. Now you could say it was M32. I mean, you could map C plus C into M32. Take two 16-dimensional projections down the diagonal, right? Put 16 ones and 16 zeros for one of them, and then 16 zeros and 16 ones for the other one. But the simplest one, and usually the simplest one is the answer, unless you're Sherlock Holmes. Okay, so Sherlock Holmes said you hold out to the end and you take the most difficult one that couldn't possibly. You have to eliminate all the others. Of course, it'd be the simple ones you try first and eliminate those. And at the end, I think the way it goes is, and it's a good maxim. What's left after you've eliminated the ones that are impossible, no matter how improbable, that must be the truth. Okay. Oh. That. Yeah. So all right. So we have M2C. And by the way, does anyone recognize this? Does anyone recognize this sequence of ordered couplets of numbers? So 1 and then 1, 1, 1, 2, 1. What's the next one going to be? Without even drawing the triangle, the diagram, what's the next? What's it going to be, Larry? Sorry. Well, that's just words. What's the answer? It's for the next stage. I mean, you're telling me how to calculate it. I want to get the answer. Huh? I guess so. And then I might ask you, how did you get it? You're spoiling my thunder. Yeah. Okay, good. So we can just so here's an exercise. That you do get the I mean, every stage it has to be the binomial coefficients, right? You wouldn't believe that was a C-star algebra exercise. You might not believe it. But for that matter, why is it a probability exercise? I'd like to see that. I'd like to see someone go over that. And Pascal is a famous, well, he's a general mathematician too, I suppose, but I think he's maybe best known as one of the founders of the theory of probability. Well, okay. So that's the algebra, okay? Now we could say, what about the group? What about the K0 group? Well, we know what K0 of a field is, right? So we know what the K0 group is for the first row. So that's the field. For that matter, we know it for the second row too, because it's the direct sum of two algebras, the direct sum of the two K0 groups. Do you agree with that, Carissa? That K0 would preserve direct sums of algebras? The K0 of the direct sum is the direct sum of the K0 in the sense of groups. Well, that's an exercise then. If you don't agree immediately with it, but even look, there's no easy way out. Even if you agree immediately with it, it's still an exercise. Okay. Okay. So don't forget the exercises you hand in are only the tip of the iceberg. 9/10 of your homework is just done at home. I mean, and it doesn't necessarily see the light of day. That's how I understand how to study a subject. You can, one way to study is to read a book, but I think if you're going to read a book, you should start at the end and work backwards. That's what we're doing, right? Sort of. Yeah. The AF algebra part is later on, I guess. We're skipping, in the meantime, we're skipping the Bott periodicity so far. But we should keep going over that, keep reviewing. I mean, that's one of the, of course, it's related to closely related to the AF algebra theory, even though there's no K1 for AF algebra. Okay, but it's important. It's already important that there isn't any K1 for an AF algebra. Let me just mention the fundamental, the basic theorem for AF algebras. If you have an ideal, closed ideal which is AF, that means it comes from something like a Pascal triangle. It's a whole bunch of finite dimensional algebras, and they're schematically represented by these multiplicities. If you did have multiplicity 2 here, you'd draw 2 lines. And if it's a whole lot of multiplicity is quite large, then you would just put a number beside the edge. So by the way, taking complex numbers into 16 by 16 matrices, where you put the number 1 16 times down the diagonal, that would have multiplicity 16, right? Okay. Okay, so these are the ideal is AF, and the quotient is AF. First of all, if a big algebra were AF, then the ideal would be AF, and the quotient would be AF. That's the exercise. Okay, it's a good exercise. It's easier to prove the quotient is an AF algebra than to prove the ideal is, but it's true for the ideal too. And that's a bit almost like remember, for vector spaces, if you if you have a finitely generated vector space and you want to define the kernel and you want to show that every operator has index, every linear operator has index, then you have to look at the kernel of the operator and the co-kernel and show that those are both finitely generated, right? Okay, that's what finite index means. It means the kernel and the co-kernel are finitely generated. Well, if you have a quotient space of a finitely generated vector space, then the finite generating set maps into a finite generating set, maps into a finite set in the quotient, which will be generating. That's a no-brainer, okay? But nothing personal meant. But if it's a subspace, like the kernel, the co-kernel is a quotient, by the way. You take the image and the whole codomain, and you divide the codomain by the image, and that's the co-kernel. And then if that's finitely generated, you look at the fake dimension of that, and that's that's one of you look at the smallest possible number of generators, it's finite, and then you look and you do the same for the kernel, except you have to know the kernel is finitely generated. Okay, so it's a subspace. The only way you see immediately something is finitely generated, if the big space is if it's a quotient. So you take the subspace and you describe it as a quotient. In other words, you construct a complementary subspace, another subspace, such that the direct sum, the intersection is 0 and the sum is everything. So the whole space is the direct sum of the two subspaces. And it doesn't matter well, the way, how do you do this? It's the same procedure. It's a trivial procedure. It's the same way you construct the basis. Okay, you just it's a slight it's just that's a good exercise to remember, review how you do it, but it's not one of the big theorems of linear algebra. It's just an exercise. It's like the Graham-Schmidt. It's just an analog. It's a modification of what's called the Graham-Schmidt process. And but that means then that your subspace, arbitrary subspace of the finitely generated vector space, has a complementary subspace. But then if you divide out by that, you exactly get your subspace up to isomorphism, right? Okay, but then that represents that way you've described your subspace as a quotient. So therefore it's finitely generated because the whole space was. Okay, that's how you prove that index exists. and that's supposed to be trivial. The non-trivial statement is that well, what's the non-trivial statement, Abigail? In terms of the index. The index you is got by subtracting the these two numbers. And so what if the whole space is finitely generated? Then what do you know about the index? Of course, I'm asking you something which you don't. You have. It's. I expect that you didn't learn it in previous years, because unless you had a very advanced course talking about index. Did you just say the index should be 0? Okay, well that's exactly the fundamental statement in linear algebra. That's one of 14 different formulations. Okay, and it's the index exists. That's straightforward. The whole space is finitely generated. But the fact that the index is 0, that's a deep theorem. That's linear algebra. Okay. And it's quite a strong statement, because if it's not, well, in finitely generated vector space, every operator has index 0. Every linear operator from the space into itself is index 0. And that's actually only true in the finitely generated case. If it's a vector space which is not finitely generated, then you can. It's a good exercise to find an operator, a linear operator, that has index, but the index is not 0. Okay, and that's fair game as an exercise for the weekly homework. And if you want to, I'd say it's also super fair game if you want to write an essay where you take a random selection of these implications between two non-trivial linear algebra statements, and not throwing too much into, not making it a loaded question, not making the statement. I mean, if you talk about the null rank nullity, and you define the rank and the nullity as dimensions, well, that's cheating, okay? Because that's assuming that dimension makes sense. But that's one of the deep theorems. You want to use rank nullity defined in terms of fake dimension to prove that the fake dimension is real. Does that make sense? The fake dimension is just the smallest number of generators. So rank and nullity, you have linear transformation in a finitely generated vector space. So the nullity is finite in terms of, since there's a finite set of generators, the fake dimension is the smallest number of generators. That's finite. And for the rank, that's the image of the operator, and that's a subspace, so it's finitely generated, and so it has a fake dimension, and rank, and so you rank, and then the whole space has a fake dimension. So you've got 3 numbers, and there's a formula. And actually, if you look at that formula, then what it says, I'm letting the cat out of the bag, but that's a terrible thing to say, isn't it? But it's an expression, just an expression. If you look at these 3 numbers combined in a certain way, in an equation, that what does Abigail? What does that equation say? Yes, it's well. I'm hoping that what you're going to say is that what it says is that this proper combination, this appropriate combination of the three numbers, the fake dimension of the whole space and of the range and the kernel of the operator. If you've expressed these as an equation, that equation just says that the index is 0, which is you don't have to call it rank nullity, you just call it index, which is that's grown up mathematics. Okay, but that's my. I figure I consider that to be my my job this year. Well, every year to introduce the world to introduce what I like to think of as grown-up mathematics to okay, well, I'm talking through my hat, right? I don't know what's I don't know what mathematics is. Don't quote me on that. Oh. But maybe I'm supposed to follow my lights. All right. Okay, but so the it's and so it is. What reminded me of this of the number of fake dimension, the number of generators, that it was finite. If it's finite for a vector space, it's finite for the quotient. What reminded me is if the algebra is the corresponding fact, the analogous fact that if the algebra is AF, it's a limit of finite dimensional algebras, then the quotient is going to be such a limit too, so it's AF. And that's easy, just like passing the quotient of a vector space, finite generated vector space. And then now it's a little trickier for the ideal because it's not there's no complementary subalgebra in general. Okay, if you had if A were equal to if there were a subalgebra of A which is isomorphic to the quotient, like there is a complement to the ideal which is a subalgebra, and wasn't it if it were isomorphic to the quotient would be AF. Well, if you knew that the in that case, well, you wouldn't even know that was an ideal for one thing. You couldn't divide out by it in the algebraic sense. Of course, if there were an ideal, if it were the direct sum of two ideals, then it's easy because the one of the ideals would be divide out by one of the ideals, you'd get the other one. Okay, and any quotient of an AF algebra is AF. But no, it's an exercise definitely to prove that that an ideal of an AF algebra is AF. Even in a purely algebraic setting, look at it as a purely algebraic exercise. So A is the union. So we're asking if if the ideal is AF. If A is an increasing union of finite dimensional algebras, finite direct sums of matrix algebras, then does that also hold for the ideal? Okay. It's you may not be able to do it. I may not be able to do it cold turkey. But it's you shouldn't always just do things that you know how to do. Or no, that's a silly thing to say. Maybe you can't finish doing it until you know how to do it. But a lot of the effort is to find out how to do it. Then, by the way, I guess once you find out how to do it, you should do it, just to nail it down. Which means writing it out and then maybe handing it in even. All right. Okay, but so the main question is that it's decidedly not an exercise, and well, it's a conceptual exercise, if you like, in K theory. It's an application of K theory, of K1, right? So on Bott periodicity. So you might think AF algebras are just K0, and that's what the classification is. But and that if K1 is equal to 0, then that's all there is to it. But in fact, you can make hay with the fact that K1 is 0. That's what implies that if the ideal and the quotient are AF, then A itself is AF, okay? And that's a rather major result, okay? It's I had proven that if there were a complementary subalgebra, which was AF, a complementary subalgebra would be isomorphic to the quotient. If there were one, then the A was AF. I had proven that. But for that, you have to show that you have a projection in the quotient, that it comes from a projection in the algebra, okay? And I didn't know how to prove that. But one day at a meeting, the famous Larry Brown, Lawrence G. Brown, came up to me, and I knew who he was, so I immediately got a bit nervous. And he said, this is after I had done the K0. Bradley had done the Bradley diagram classification of AF algebras, and without realizing it was the same thing, technically it was the same thing. I had done the K0 classification of AF algebras, but without calling it K0, just calling it very fundamental dimension, which is what it is. My point of view is the name K0 came later. Well, it did, I guess. Okay, but what Larry Brown, so some of you may have heard this historical sketch, but Larry Brown came up to me, and he said, you know, what you're doing is K0. Okay, well, I knew I should be paying more attention, but I didn't, and I just said, so. Okay. So what he said was, so there's also K1. And he knew I was trying to lift projections, okay? And he was just giving me a hint, because that's how you do it. You use the fact that K1 of the ideal is 0. You can assume that the quotient is enough to want to lift projections. You can assume that the quotient is just the complex numbers, okay? And there's a simple K0 proof that that at least the K0 class of the unit of this algebra, the projection, the K0 class of the projection comes from the K0 class of a projection upstairs, okay? Because there's a certain short exact theorem which is called the exact sequence of Bott periodicity, the short exact sequence no, it's a 6-term exact sequence of Bott periodicity. You have this is a short exact sequence of C-star algebra. So if you get a short sequence of K0 groups, short, but it's not exact at the ends. It's not exact here and here. Then you get another one for K1 because these are functors, okay? Remember, K1 is just K0 of the suspension, and the suspension of any Banach algebra is functions from the real line into the Banach algebra, vanishing at infinity. It's the soup norm. Okay, so that's but it's not neither of these sequences is a short exact sequence. But it turns out that there's an index is pertinent in the general setting of C-star algebras, because there's an index map that goes from K1 of the quotient to K0 of the algebra. Okay, and that's the even index map, and the index is even in the K0 group. Then there's an odd one too. That this is a 6-term sequence now, and it's exact. Okay, and that's Bott periodicity. That's one way of stating Bott periodicity. It's only true for the complex numbers. So the index map exists in the real case too. The even index map, but the odd index map requires the complex numbers. All right. Well, let's start fitting things in. If it's if the quotient is AF, then this is 0, okay? The K1 of the quotient is 0. And K1 of the, I'm writing these left to right. Sometimes people write the second row right to left. That's because they don't realize that this crossing over graph is can be embedded in the plane. There's a way of writing, there's a way of drawing it so the lines don't cross if you object to that. Anyone see it? How you can write this, all these arrows in the plane without a crossover. Okay, well, okay, that's a planar topology exercise. Don't tell anyone this course doesn't have topology. All right. So all right. So we have but what that means is that well, the important thing is the K1 of the ideal is 0. What that means is that yeah, you have a map upstairs from the big algebra to the K0 of the big algebra to K0 of the quotient. If the next arrow is 0, just the arrow itself, not even the codomain. If the next arrow is 0, then what does that mean in terms of exactness? How many people have that at fingertips? What does exactness mean? Larry, do you know what exactness means? Charlie, do you know? Yeah. So yeah, and the kernel is everything, right? If this map is 0, its kernel is 0. Therefore, if you have exactness exactly here, then the kernel, which is everything, equal to the image of the preceding map. The image of the preceding map will be everything. So it's in other words, it's surjective. Now we want to prove surjectivity at the level of projections, right? But at least you get surjectivity at the level of K0. Any K0 element comes from a K0 element. Any K0 element here comes from a K0 element. That's what this says. And that's Bott periodicity, okay? And the rest is just mopping up. Going from K0 elements to projections, to positive K0 elements to projections, that's really it's just cleaning up after a good day's work. Some people were repairing the roof outside my office. They left a pile of trash outside my window. I wish they'd come and clean it up. I could tell them to try and use Bott periodicity. The periodicity would be seeing them come back. I wish. Okay. How are we doing? Well, how did I get into Bott periodicity? Well, it's AF algebra. I was trying to persuade people that there's nothing wrong with starting at the end of the book. And we've got a description of the algebras, a limit, the Bartley diagram algebra for the Pascal triangle. And the question is, what happens at the level of groups? Well, if you take K0 of the complex numbers, you get hands up. What's K0 of the complex numbers? And this is only people who don't know, right? Okay, everyone knows, good. I can just say, all right, so Z, and then Z plus Z, okay? With and the K0 map, it's a functor, right? So you have a multiplicity 1, well, it turns into multiplicity 1. A map from Z to Z has a multiplicity. What you multiply by. if they either multiply by 0 or by 1 or by 2, or and if it's a positive map, if it preserves order, then it's a positive multiplying by multiplicity is positive, okay? Including possibly 0. But if the unit goes to the unit, then it's well, we've decided the diagram is this, and that means the map is non-zero, multiplying by 1. And at the next stage, well, again, we have a z on the outside, 2 z's on the outside, and what do we have in the middle? What's k0 of matrices over complex numbers over a field? Okay, sometimes it's easier working with idempotents, okay? This is slightly tricky to show that matrices have the same k0 group as the algebra you start with. Take matrices over an algebra, ask what that algebra has for k0. Well, with the modulo definition, you have to, that's a good exercise to work it out, okay? But for idempotents, nothing could be simpler, because if you look at the algebra, then you look at idempotents. This is in the unital case, right? If you look at the algebra, then it's the k0 is idempotents, equivalence classes of idempotents. Well, that you may not be able to add always, but then you look at matrices. You look at idempotents in the matrix algebra instead. In addition, and you think of the algebra itself as sitting in the upper left-hand corner. So you get more and more idempotents as the matrix algebra gets larger and larger. But suppose you, okay, so you look at the 1 by 1 matrices, 2 by 2, 3 by 3, and so on. But suppose you throw away the 1 by 1s and the 3 by 3s, and you just look at the 2 by 2s and the 4 by 4s and the 6 by 6s. Okay, then those are matrix algebras. It's the same. It's the same. You're just taking the union, so you get the same idempotents. It's the same algebra. Okay, the union of the algebras is the same whether you take all of them or just the even numbered ones, right? But then even numbered ones are exactly matrix algebras over the 2 by 2 matrix algebra. So that means that the 2 by 2 matrix algebra, when you take matrix algebras over that, you're going to see exactly the same idempotents and the same equivalences. So the k0, the Murray von Neumann semigroup is the same idempotents and equivalences. Maybe the Murray von Neumann is the self-adjoint case projections, and then Kaplanski did it for the non-star case, the Kaplanski Murray von Neumann semigroup. How many people recognize the name Kaplanski? Somewhere there's a chart, there's a board on the wall showing the early history, at least of the, well, of course, just the early history of this annual Putnam competition. Well, the very first one, who won the very first Putnam competition? Well, how many names have I mentioned in the last 2 minutes? Yeah, okay. And who do you suppose, and what team, what university team do you suppose won the first Putnam? Team of 3. Well, yeah, we're here. This is it, yeah. And it went back and forth. Of course, there's a slight sort of fly in the ointment. What was the prize? The prize was not a scholarship to U of T, it was a scholarship to Harvard. Well, fine. Okay, but the next several years, the winning team and the winning person, I believe, as I roughly recall, just moved back and forth between the 2 places. And Kaplanski took the scholarship to Harvard, and one of his students was someone who's well known in the area of popular entertainment. Maybe still maybe The name still resonates now. How many people are familiar with the comedian, perhaps Tom Lehrer? You can look it up. Tomleher. There's another related question. How many people are familiar with the Canadian comedy team, Wayne and Schuster? Well, again, that's before. It's not before my time, but on the other hand, it's they're famous enough that they're worth looking up. Wayne and Schuster. Okay. Oh, all right. Well. Okay. And but when they were well, they formed a team already when they were undergraduates here. But at the undergraduate level, it wasn't Wayne and Schuster. What do you suppose it was? Huh? No, well, that's a good point. It wasn't alphabetical. The Wayne and Schuster are not alphabetical, but it was even less alphabetical when they were here. It was Wayne and Schuster and Kaplansky. Okay, so that's a morsel of history, if you like. But Kaplansky of course, had an illustrious career. He was head of the mathematics at the University of Chicago, and he was the first director of Mathematical Sciences Research Institute, Berkeley. And he was, I like to think that almost first and foremost, he was an operator algebraist. And once you talk about the Kaplansky-Murray phenomenon equivalence, then it's clear it's not just C-star algebras, or phenomenon algebras, it's just algebra, or algebraic geometry, if you like. Well, okay, so that's so in the middle, it's how many people don't know again? Okay, everybody knows, good. All right. And you can put dots if you don't want to write anything more, or don't have time. Okay. Did someone just come in and then leave again? That maybe was going to take over, wanted to take over the room. They came in and they saw us in action and decided it was too risky. Okay. Okay. We'll be happy to carry on discussion in the hall.